Okay, so I'm going to share my, let me start recording, share my screen. So, where were we? Okay. Yeah, so I had last time, so you're all there, you can hear me, correct?
Yes, sir.
Yeah.
Yes, sir.
Yes. Okay, so you could mute your thing, and unless you have some question, when you can unmute when you have a question. So we had seen how to model sequential systems in a modular way, and last class we had started discussing how to model concurrent systems, and before, also in a modular way, in the sense, if you had transition systems to some subcomponents of a concurrent system, how do you do do it in a model for the composite system? How do you compose the transition system for subsystems into a bigger transition system that models the behavior of the entire system? So before I introduce the formalism, let me take a couple of these examples. Okay, see the three examples that you see here on the top, except for the thing, they're all instances of concurrent systems. So let me take this hardware circuit example. Now, a hardware circuit, and even embedded system, and so is this system that you see of the traffic light controller. They're all embedded systems, and there, usually what you have is the actions, the concurrent actions in the system are synchronized, or they're all synchronized with respect to a global clock. And the global clock could be implicit or explicit, okay? So for example, in this hardware circuit, you have this two state holding devices, which are usually called flip-flops or registers. Okay, and they respond. I mean, the system changes state every time the clock ticks, advances by So the clock is a kind of a repetitive event, or things that go up and down in regular interval. So the assumption is that the state only changes every time the clock here ticks. And so here there is an environment. So a reset, which is kind of also, now the environment may change on its own, okay? But because the rest of the system changes only when the clock changes, pretty much, even if the environment changes on its own, the system as a whole, changes only when clock changes. Okay, I mean, more specifically, these states holding devices change when the clock changes. Therefore, you might as well consider the environment kind of changing. It may change more often or more delayed in a fashion. But the important thing to notice is that they're all governed by, the state changes are governed by a global clock. And when that changes, every component in this system that is operating concurrently changes simultaneously. For example, if the clock changes here, whatever the environment is, the reset value is, then B and A are updated, based on whatever the current value of B and A are, and whatever the environment value reset is. Similarly here too, okay? So the inputs here might be some sensors giving, whether there's a car or not, and then they kind of, change the two the controller itself that is controlling the two lights here change in response. So the current state is the state of the lights, the two lights, and the environment here is if there is a car that is present here, or maybe even when there is no object, a car, maybe it will change or or not. Okay, so there is some environment and there are states. Now contrast that to the system here, the multi-threaded concurrent program here. Okay, so there I'll ask you questions. You're probably familiar with concurrent programming like C11 and so on. So here there are 3 threads. Okay, and each thread consists of a sequential program. Let's suppose that your initial state, in the initial state X and Y, there are 2 variables, X and Y, which both of which are shared among the 3 processes executing in the 3 threads. Suppose the initial state, in the initial state, X and Y are initialized to 0. What do you think is the output here? Erimalai, would you fathom a guess? So I'm saying, what will be the output at the end? So these threads, these processes are all have finite number of statements that they need to execute. So when all the threads are the threads are executed, and you reach the end of all the processes, I'm asking you, what is the expected value of X and Y?
It depends on which thread executes first and which executes the order of execution of the threads.
Correct.
But
yeah.
But we can say that the value of Y will be 20 or 21. Those kind of.
Correct. So you hit the nail on the coffin. Yes. So the answer would depend on the scheduling. Okay. Which thread, the schedule that is used to schedule these processes in the 3 threads. Correct. That's what you meant. So So I mean, give me one possible value.
X equal to 10, Y is equal to 20 is a possible.
X is equal to
10.
Okay, and
Y is equal to 20.
Yeah, and what schedule of the 3 threads that would result in possibly result in that final state?
So one possible order of execution is first thread 2 is executed and thread 3 is executed, and then thread 1 is
correct. Thread 2 is executed completely, thread 3 is executed completely, and thread 1 is executed. Notice that is not the only thing. I mean, these things, the individual statements that occur in each of these threads could be interleaved at any level of granularity, correct? So there is another aspect, okay? There is a schedule, but what is being scheduled? Sometimes, I mean, there is what the atomic actions are also important to recognize here. If the atomic actions that are used to determine the switching of context from one thread to another context is done at the level of each assignment statement, that also is a factor, okay? So you could even have, I mean, you gave the example of where thread 2 and thread 3 were completely scheduled to their end, to their conclusion, I mean, to their end before thread 1 was scheduled. But that is not necessarily the case. If the atomic action is the individual thing, I mean, the scheduler, which is the operating system here, could schedule one assignment from thread 1, then do thread 2, and then do thread 3, and then get back to thread 1. And so there are various possible interleavings, okay? And the and so, and the level of granularity at which these threads can be interleaved depends on what is the atomic action. Sometimes the atomic action could be at a complete assignment statement, or sometimes they could even be considered, depending upon at what level of abstraction that you actually model the reading. I mean, because each assignment statement, when it is actually implemented in real systems, you usually do a read of the memory where X is stored, and then a read of all the right-hand side variables, and then you compute and then you assign. So if indeed, so the atomic, which is the atomic actions and their granularity is very important before you can actually determine the thing. But the point I'm making is, you see, the way that these things, the three threads are composed here is different than the way these the components in asynchronous. The first two examples are instances of what I call synchronous systems, okay, where there is a global clock and that synchronizes all the events, and all the concurrent components are updated. The states of the concurrent components are updated simultaneously, whereas in a system of this kind, which is usually referred to as an asynchronous system, there is interleaving. There is a hidden scheduler which is supposed to pick one of the processes in the atomic action from one of the processes to, it picks one of the process and determines how many steps of atomic actions from that thread need to be executed before you you schedule the other one. So when you model these things, so there is a lot of these hidden things. For example, in the case of synchronous systems, there is this hidden clock, okay? And therefore, how you model and how you compose these transition systems, it depends on whether your concurrent system is using a synchronous paradigm or an asynchronous paradigm, as in these thread things. And therefore, the rules of composition of transition system for concurrent systems is based on, needs to take into account the whether you're doing the using a synchronous paradigm or an asynchronous paradigm, of course. And and then there is another angle. I mean, do you need to model the clock itself, or in the case of asynchronous system, do you want to have the actual scheduler model? Because the actual schedule used, because there are so many aspects. For example, in concurrent, the OS could give certain priority to certain threads, and it can be using various scheduling policies such as round robin and various things. So sometimes, so one can choose to model explicitly the scheduler, okay, but usually that is not done, and you may not want to do it. You want to abstract the scheduler and say, oh, I want to analyze the behavior. I want to develop the model by completely abstracting the scheduler, and assume that these threads can be, the atomic actions can be scheduled at, I just want to model all possible interleavings. And since the scheduler is not really visible for various applications, and if you want to model at the application level and you want to guarantee certain predictable behavior, maybe you need a way in which you abstract the scheduler and then do it. So these are some of the technical points that you need to consider in modeling concurrent systems. Okay, so let me get to this multi-threaded example again. So, as Erumalai pointed out, so the outcome of this, the final state of this is scheduler dependent. Would you normally write concurrent programs that way? Amin?
I'm not sure. I'm not familiar with concurrent programs.
No. See, so what happens
think
is this, the behavior is unpredictable, no? So if each of these three, okay, obviously these three are being, you need to coordinate them, no? So see, this is a typical example. I mean, so I'm going to tell you, I'm going to answer the question. So you're right. I mean, that this is a situation where what is called, there is data race, okay? Because you don't know what the outcome is. See, some unpredictability is desirable, okay? Maybe that you do, but usually you want, if there are shared resources, and if those shared resources, here X and Y are shared resources. And when for shared resources, you want to be careful. You want to, if you want predictable, if your data races are usually not desirable, okay? Because they introduce certain level of unpredictability, okay, in concurrent programs. So usually shared resources, access to shared resources has to be done in a synchronized fashion so that your outcome will be predictable. Maybe a certain level of unpredictability might be desirable, okay? But still, generally, you need to have some synchronization primitives, okay, in order to, in the absence of knowledge of how the scheduler will schedule, if you still want to write concurrent programs, that's why all concurrent programming languages provide what are called synchronization primitives, okay, which will, using which you can stop, you can block your thread, okay, and unblock it, okay. So usually you provide, they provide, you must have, I don't know, if some of you might have done, I don't know, concurrent programming, they provide things like semaphores, you usually in waiting primitives, blocking primitives, etc. So that, you need to use, you will use them so that even though at an application level, you don't have the knowledge of how the scheduler might schedule it, you will, you still have to write programs such that they accomplish things. For that, we usually use special concurrent programming languages provide special primitives, okay? So, and so when you model these languages, just like you have while construct and if then else, we use that to model the transition systems. When you compose concurrent systems, especially asynchronous concurrent systems, you need to, define the meaning of these synchronization primitives, which is what we will do at a certain level to give you an idea of what is involved in modeling concurrent systems. See, whereas for synchronous systems, you don't need such any elaborate synchronization primitive. Why? Because the clock is already there, okay? See, the assumption is that all the concurrent systems will change simultaneously at a certain tick of the clock, okay? Therefore, so you don't need to do it. I mean, you don't need any other special primitives, and you will see that it is somewhat easier to compose synchronous systems, okay? With this introduction, I'm going to now show you a formal way of constructing a formal modular way of constructing a transition system for each process in a concurrent system, and then show you formally how you can compose transition system in these two dominant paradigms of building concurrent systems, synchronous and asynchronous paradigm. Before that, do you have any questions about this informal introduction to concurrent systems? Any questions? Okay. Let me now move to this. Yeah, I think I've said most of thing. Okay. Yeah, and I don't think I need to go through this. Okay, so let's see what is a synchronous transition system composition. You have seen this example. It's the mod 3 counter. Okay. And here, remember that we modeled usually the reset signal, which is an input to the system, which is actually not controlled by the mod counter system itself as part of it. Okay, so here what I'm showing you is an environment which actually controls reset, which changes reset, and this system which is uses a reset as an input and changes its internal state, the state of the counter. So the environment also I'm explicitly showing here as a system, which in this case I'm forcing the environment such that you start, this is a crazy environment, okay? I mean, you could say it's crazy because it starts with an initial state where reset is 0 and then keeps reset continuously 0, okay? So the question is, how do I, now you remember that this system on the right side, because reset was the input to that system, we had modeled it in such a way that reset could change arbitrarily because that was not under the control of the mod counter to change. So the behavior of that mod counter accounted for reset changing arbitrarily by an environment. In that sense, the mod counter was an open. The modeling of the mod counter was was an open system. Here, I'm trying to say if I had an environment also specified as a transition system, which is now I'm showing it graphically here. The question I'm raising is, how do I compose these two systems, assuming that the composition paradigm that we're using is a synchronous paradigm, okay, in which I'm assuming that there is both the systems are changing under the control of a global clock. Okay, so how do you think, before I introduce the formal rules for composition, if I had an environment which is changing reset the way that I'm shown, okay, how do you expect this composed system, the closed system with the environment and this thing to behave? Ratnakar?
That at the end, the closed system?
Yes.
Could you repeat what you said near the end?
Yeah, what do you think, how will this composed system with this kind of an environment, see the environment here, I'm constraining to keep the reset permanently 0, okay? So if I keep the reset permanently 0, what I'm asking you, what is the combined behavior of this system. When you compose this environment with the mod counter system that I've shown on the right side. So basically, I'm asking if in the environment I control the reset to be constantly 0, what is the combined behavior of such a system?
It's just a clock. It goes from 0 to 4 and repeats cyclically.
Correct. So you see certain behavior will be eliminated, correct here? Because this open system of the mod counter, I had given certain transitions here, which allowed for a reset being asserted, becoming 1, okay? So basically, you start with 0, 0, 0, because this initial state will not even be possible, because my environment is starting with reset being only 0. So you will see this. So, I mean, I hope you see my cursor. So it'll start from here, this initial state, the other initial state, the other arrow here, where the reset is 1 will not even be possible because the environment is not even allowing that, okay? And so you will, as Ratnakar observed, so you will just go through this path, okay? From here, it will continue to count and then go back, okay? Just this one. 0, 0, 0, 1, 1, 0, then 1, 1, bang, it'll go back here, okay? So when you compose it, that is the thing that you have, okay? So what we want is to have a way of composing, okay, this thing, given the transition system on the left side and the transition system on the right side. So the right side transition system you had already seen earlier, okay? The symbolic representation of the transition system for the mod counter, what I consider as the open thing. So where it was not controlled reset, although reset by convention, we made it as part of the state because we included the input also as part of the state. Therefore, this is what we had it, correct? So I'm just repeating that thing. So now the environment here is the one that controls reset. So you notice that the transition system for the mod counter does not influence S at all. It uses reset to determine the next state, next values for A and B, but it never constrains reset. That's why I call that as that reset is an input to this thing, okay? So whereas the environment now here is the transition system is constraining it, okay? Because it has an initial state in which reset is 0. That's what is asserted by this part. And the transition relation corresponding to this is exactly, it just keeps reset the same, okay? That's how I'm defining the thing. Now, what we need to have is determine a general rule wherein if you had two transition systems like this, you will be able to just construct a formula which puts these two formulas for these individual transition relations, systems, and then constructs the thing, okay? The combined transition system, which should behave like how Ratnakar described, okay? What is that rule is what I'm going to show you, okay? So this basically what you do is you start each system with their respective initial states. And then you construct the combined transition relation such that you will get the effect of marching both these systems in lockstep, okay? And that's how we're going to be doing. So what you have is each of the systems has its own set of states, and this the state, the state, the universe of the combined composed system is the cross product of all these states. Okay, and the formula for the combined transition system is just a conjunction of each of the individual transition relation, the transition relation, because what you want is, what you have is something like this. So there are two transition systems, like I'm shown on the right side, TS1 and TS2. This has some inputs that it is coming from the other. Each has some inputs which are coming from the other things, and there could be some environment inputs that are actually coming from the environment. But the most important thing is you are marching both the transition system in lockstep, and that's why that can be represented in your as a formula by asserting that by making a conjunction of each of the transition relation, of each of the components. Here, I'm showing it in general, assuming that there are n subcomponents. Okay, then you just take the composition of all the things. Now, there is a bit of thing. See, I mean, there is a little bit of a technical difference that I'm showing here. Okay, so you could either include, see, the way that the convention that I used is, if you include the inputs as part of the state, the input of every subcomponent as part of its state, then you will have, that is one way to do, which is the way that I've described. But sometimes in the picture here that I've shown, sometimes what they do is you include only the state components and not the inputs. Okay, that input will come from the thing. But let's stick to our convention. Okay, so if you stick to the convention that I have shown you, wherein you include the input as part of things, then what you will have to do is you will have to also add this constraint that your input will be the same as the output coming from the other side, or you will have to kind of have only one copy of the inputs. Okay, so the initial state is a conjunction of all the initial the formulas giving the initial state. And since I'm assuming that these some of these things will be repeated, like in this case, for example, reset was there in the environment transition system, as well as the mod counter. Therefore, if you use that convention, then you will have to make sure that you constrain those two resets have to be the same. Okay, and that's what I'm making in this in-out constraint. Okay, and similarly, what I'm claiming is that then you can construct the transition relation for the combined composite system by just taking the conjunction of the formulas of the representing the individual transition relation, with the additional assumption that these repeated signals are, the state variable components are identical. So, for this system, what you have is, so your combined synchronously composed transition system its state will be a cross product of these two things, and your initial thing will be just whatever the initial state of this, the environment, what the environment is, which is not a preset, and whatever the initial state is. And with the additional thing, look, I had included reset here as well as this, and you have to assume that those two resets are equal. So by virtue of the fact that you're taking the conjunction of these things, you are eliminating this initial state from the initial state in which reset is 1 from your combined system. Is that clear? So that is, because the initial state is taking a conjunction, it is constraining. It has to be something. So the combined initial state has to be something which is consistent with each of the initial states of the system, whereby it is eliminating this particular initial state in the the mod counter translation. Is that clear? I want you to be sure about that. Okay. So
Sir,
yes.
could you say once again what it means to march each of them in lockstep?
Okay, what that means is you are at any particular state. What it means is that if you're in so start with initial states. So the initial states are the state in which the each system is the initial state of the combined system, which is now is a cross product, okay, over both. I mean, it's a cross product of the states of the two things. So you understood what the combined initial state is, correct? So the combined initial state is constrained to be is such that both these conditions are valid, okay?
Yeah.
And that means that you can have A is equal to 0, B is equal to 0, and reset has to be 0, okay? The reset, the S1 reset and S2 reset, okay, they are identical, I mean, they're equal. So it is 0. Now, once you have the initial states defined, this transition relation, which you get by taking the conjunction, what lockstep, informally what it means is, you have to now make both these, the transition relations, you have to march the two components such that both are, the transition relation as constrained by the individual transitions, the individuals have to be preserved, okay? What does this say? Okay, so because this says, the environment says, my next value should be of reset should be 0. Okay, so here, so since I've already constrained it to be 1, so I will take this transition of the environment transition as well as this arrow. There are two arrows here from reset 0 to 0, the environment transition, as well as the transition from the other one. Both those will take effect. Okay, that is what I mean informally when I say it is lockstep. Okay, it is not like, you will see later in asynchronous system, you could just march one of them, whereas here you're forcing both the systems to take its individual transitions simultaneously and concurrently. Okay, so you will have to, the next state of the combined system will be the effect of making the environment take its transition as well as the corresponding transition that is possible in the thing. Therefore, it'll make reset become 0, and here that will mean that it'll make this go to 0. If in this case this is the only transition that is possible, maybe even with this constraint, maybe there could be multiple transitions possible. Okay, so in which case all that will be considered. That's what I mean by lockstep, that both the transitions, transitions of every individual components will have to be made to take effect. Okay, that's what is happening. Okay, so this one, the environment is changing. In this case, it is modifying the reset value. In this case, it stays the same, and simultaneously, this one is making its transition march forward, okay? And that's why you will get 0, 1, 0, okay? So that's what this, so the formula that captures the lockstep semantic in which you're forcing both the transitions to take effect is done by taking the conjunction, okay? Because you're saying, oh, that part of the state of what this component has to be moved as per this transition of the mod counter. And similarly, the environment has to be made to march ahead as well, as per the environment transition. That's what I mean by lockstep. By lockstep, what I mean is both the transitions that are possible by the individual subsystem have to be made to take effect. Is that clear?
Yes, got it.
And the important thing is, when I say lockstep, that's an informal concept, okay? But here, I have formalized it by taking the conjunction, yeah? Now, this portion here that I have here is kind of a, you could say it's a baggage, okay? Because I'm repeating the reset to be part of this as well as here, that's how I'm taking. Of course, there is an optimization, like I said, you could include only the, if you take a global picture, once you know when you resolve all the inputs, outputs in the global context, then you could define the individual transition relation such that you will read the inputs from the other transition system, but you will only change the state component corresponding to this. So therefore, then you would not need these input-output constraints. But if you really just repeat those things and take the cross product, then you will need this to be consistent. Okay. Now, let me ask a question to Amin. Okay. Let's suppose that I made the transition system, maybe advertently, usually inadvertently, I changed the reset. Hey, there is a way you have to make sure, okay, so because I'm including the reset, suppose I deliberately, mischievously, if you want, if you will, I changed the reset. There's nothing that prevents me from defining the transition relation for the mod counter in which it changes the reset, correct? I mean, suppose I did that. What will happen when I take this conjunction? Suppose I make, this one is saying reset will remain the same. Let's suppose I say here, reset will change from 0 to 1. Then when I take this conjunction, what will happen to the combined transition relation?
It will be false, right?
Exactly right.
Already given equal.
Exactly right. So it will become false. So that's why. So you will have to make sure that what you consider as inputs to a particular subsystem should not be changed, okay, by the transition relation in that system, okay? Now, because I'm including it here by convention to make it simple, that's why I'm, so you'll have to make sure that the transition relation when you define doesn't change its inputs, okay? It only changes its own state variable. It can read or it can use the inputs, okay, to determine the next state value of its state variables, but it should not. So if you use this convention here like this, you have to make sure that you don't inadvertently or mischievously change the inputs in your subsystem when you define the transition relation of your subsystem. That is a convention that you'll have to follow, okay? Any questions? Okay, so that's how you do. So in a sense, what I'm saying, another important point is that if you've already had subsystems defined, a transition relation subsystems, you don't need to start from scratch in order to define your combined composite, the transition relation to the combined system. It's easy. You just make the state universe to be cross product, and then you just take the conjunction. That's it. Yeah. So it is. You can see that it is quite easy it's quite simple to do, and that's what I mean constructing in a modular fashion. Okay.
So,
yeah.
So model checking tools require these kind of models to have a transition relation to it total, right?
Yes.
But we cannot guarantee that when combining these.
No, but if each individual transition relation is total.
Yeah. So my question is this: while making this synchronous composition, and there is no way
the assumption is that each individual transitions relation for the individual subsystem would be total. Okay.
Okay.
Yeah, I mean, assuming that we follow that principle in constructing all our transition relations, even in subsystems, then your combined transition is guaranteed to be total, left total. Yeah.
Yeah. Okay.
Okay. So now let me get to doing showing you for the asynchronous composition. Okay. So here you would have probably already guessed. Okay. This is a little bit more liberal. I mean, synchronous composition, I said it is making you take both the transitions arrows, the steps. Whereas here, as Irmalai, pointed out, as we discussed earlier, asynchronous composition allows all possible interleavings. Correct. So if you want to model the combined the composite by abstracting away the scheduler, how would you do it? Ratnakar?
I think the composition will be similar without the condition that we enforced previously.
Which condition?
Like in the previous synchronous composition condition, we demanded that S1 dot reset is equal to S2 dot reset and so on. I don't think we will add those conditions here.
Well, is that well? Okay. Is that enough? Okay. So you're right. You're commenting about the shared part of the thing, but think about, will an and work? Okay, because and will force you to see here. We want the interleavings, right? So you want to allow for any single step in any of the threads to be scheduled.
Right, then my solution won't work. It will only allow atomic threads.
Yeah, it'll force you to march, and therefore the and also will not work. Okay, I mean, you're right. The shared component, you will have to deal with that. Okay, just like the shared component here is the inputs. Okay, in each of the systems. So let's see how we will deal with that there. Okay, but the important thing is this and is forcing both the transitions to happen, which should not happen, because here when I say, I will schedule thread 1 and not thread 2, so I can choose to do one or more, actually, yeah, in thread 1 when I schedule it, without actually marching any of the other threads. So that's why asynchronous system behavior, asynchronously composed system behavior allows for individual process, just a single process to be scheduled. Okay. As a matter of fact, if you abstract away the thing, it will it should only schedule one at a time. Okay, that is the thing. Now, maybe you can have different paradigm in which some of them are synchronous, some of them are asynchronous. Okay, I mean, you can imagine those things, but traditionally, what is by when people say asynchronously composed parallel processes, what it means is at any particular point, you choose exactly one process to advance, okay? And that is one. And the question is, what is the formula that will capture the effect of marching a single thread or a process? I'm using thread and process interchangeably here. So firstly, so here I'm throwing away the input-output concepts, okay? So, I mean, that is the shared, is the thing, but the shared thing can be modified by any of the processes, okay? So whereas there in synchronous composition, we impose the convention that, okay, the inputs you can only read, but not, modify. Here, we are not using the input-output, the shared components can be, and there'll be some local component which is only modified by, which is accessed and modified by individual threads. And there'll be some shared components which can be, which any thread or process is at liberty to modify, okay? So the process state, individual transition system state will have a local component and a shared component. In this particular example, there's no local component because X and Y, the two state components are both just shared. So we model interleaving of process actions consistent with an arbitrary OS scheduler, okay? And that by the interleaving semantics, we assume that only one thread can be scheduled at any particular point. Yeah, so and we model it such a way that any arbitrary interleaving is possible, which effectively means the scheduler is completely abstracted. And we will see, we'll use non-determinism, to define the combined system. Yeah, and then you will have to also first, determine what your atomic actions are, because that very much depends on how you define this interleaved semantics. So for now, let's assume that we are doing it at a statement level, okay? Each statement in a program. So given that, so here is the formal way to symbolically model this asynchronous composition. Basically, what you will have to do is you have to say that the combined transition system will be S cross S. Okay. So what will happen is each TI will have its local component and shared component. Okay. And when I take this, you will have to make sure that your state S has all the local component, and the shared component is you'll have only a single copy in this S that you have. Okay, so that is the assumption that I'm making, and your transition relation will be a cross product of that. So it'll have all the local components of every subsystem and one copy of the shared component. And this semantics, okay, while you choose one, but some arbitrary process, arbitrary transition system to march, to advance, is captured by a disjunction. Okay. So here, look at what I'm saying. So the next state is defined by the individual transition system. Okay. I can pick, if I pick the first one, I keep all the variables, all the state variables in the other components the same. Okay, and that's what I'm doing. So this captures, but I can choose arbitrarily any one of these components to schedule. Okay, so is this, or with this constraint that if you choose a particular component to march ahead, then you will have to keep the other, the local components for the local part of the state of all the other components the same. Gets you the effect that you're scheduling exactly, you're scheduling one process to march ahead. And then I'm using a disjunction here, because disjunction will give me all the possible, it takes kind of the union of all the possible interleavings. Okay, so this will take the effect of, I could choose non-deterministically, arbitrarily, which any one of the process to schedule. So that's how you construct the thing. Yeah. So here I'm assuming each individual process is modeled as a sequential process. Okay, and it has its own PC and its own variable component. And I'm assuming that all the shared components are captured by a single copy here. Okay, so that's how you model it. Let's take an example. Okay, before I use the example, here is I will do it by introducing. This is the okay. So this is a general thing. Okay, whereas here the lockstep semantics that is used in synchronous composition can be modeled by taking conjunction, whereas here the semantics of asynchronous composition, wherein you choose exactly one, but an arbitrary process to do, is modeled by a disjunction, and that's why there is non-determinism. Which one you pick is left non-deterministic. Okay, and that's why you will have n possible next states corresponding to each of the possible process that you can choose to schedule next. Okay. So before I actually show, so the in terms of code, so there are these synchronization primitives. I remember that I mentioned synchronization primitives earlier that you'll have to do, that usually concurrent programming languages use to constrain access to shared resources, such that you can avoid data races. Okay, and there are various different programming languages provide different way of blocking the process and so on. But some very common things are these things. So usually you find something called a wait statement. A wait statement, it waits until it kind of it makes a process wait at a location. Okay, it kind of busy waits in the same location until waits for a particular, until a certain Boolean condition holds good. Okay, it waits until for a Boolean condition to hold. So, which means the and you can see the piecewise transition relation, like we define for sequential program. We define it here. So the effect of this is a pre-label and a post-label. The effect of wait is it'll if B does not hold good, if the Boolean condition does not hold good, then nothing changes. the PC remains in the same location and the variable changes. That does not change either. Okay, but if B is true, then it makes the process move ahead to the post label given by I prime. And usually programming languages also provide a couple of other ways of blocking the process on a lock variable. So this is wait is based on a Boolean condition. A lock is usually done based on a shared lock variable, usually called a lock variable, or sometimes it is also called a semaphore. Okay, so a variable called V, a variable V. And this has the effect of, if it is, it waits, it blocks the process, it keeps it waiting until B becomes 0. That means if B is not 0, then it keeps it waiting. Okay, if B is equal to 0, then it marches ahead. Similarly, unlock, then you can lock a particular, you can lock advancement relative to the value of a particular variable being 0 or non-zero. Okay, so let's look at this thing. Okay, now here, so I'm going to show you how to construct the combined transition system for two asynchronously composed threads or processes. So here we have two identical process. Okay, they're just one of them. I mean, they're pretty much identical. So it's basically what I want to do is to constrain access to a particular location. So you see this one, there is something called this location CR is a special location where I could be changing some shared thing. So I want to ensure that each process starts with an entry point and goes through something called a non-critical point, and then advances to the critical section and keeps doing it, okay, forever. What I want to do is to ensure that it is never the case that both these processes can be simultaneously at the critical section. Okay, so I want to ensure that so each process is, there's most one process will be at this location simultaneously. And the way that I want to do, and the way I'm doing it is by making this process 0 wait until I'm using a turn variable, which is a shared variable, a semaphore, and making process 0 wait until turn is equal to turn is 0. Okay, and the other process will wait until turn is equal to 1. And once I enter the process 0 enters the critical section, and because turn can be either 0 or 1, and therefore CR, they can be only 1 at this critical section. So once I enter the critical section, I make turn to be 1, so that I let the other process allow the other process to enter its critical location. Okay, and that's how I'm using. So this, I mean, if you've gone through concurrent programming, you would recognize this. Okay, it's usually called semaphore-based mutual exclusion enforcement. Okay, so is that, so what is our goal? Okay, so before that, so is that clear? So that is my goal. Okay,
so I had a doubt. Do we do we change turn equal to 1 after we exit the critical system or when we enter the critical system?
Yeah.
Shouldn't we
So,
like
yeah,
change
but
it to
here,
1 when we exit?
yeah, here the critical section does not have anything meaningful at all. Okay, so it has only one statement. Therefore, you could say that. I mean, see, your question is usually there'll be some sequence of statements, okay, that you want to do in the critical, when you're in the, there's a critical region, okay, that's why it's called critical section, okay. So, and you have to change turn to be the value of turn at the end of that critical section, because here the critical section is a single statement. Therefore, you know, that question that you asked, while it's relevant, is kind of moot, okay? Because there's only one statement in the critical section. So as soon as you enter it, you're changing it, okay? So, I mean, so here, there's no shared thing that is being protecting. I mean, I'm only doing it, but as soon as I enter the critical location, I'm just changing it, I'm exiting it, okay? Therefore, I'm setting turn is equal to 1. So you're right, the answer to your question is yes, you have to do it at the end of the critical section, but because there's only one statement, your critical section here is of length, region is one statement. So I'm just entering it and then immediately leaving it by changing the value of turn. Yeah?
Yeah, good.
Okay. But what the observation that you made is correct. If there are multiple things, then you will have to do it at the very end. Okay. So because you want to ensure that you know, for the entire region fragment of critical sections, for all those locations in the critical sections, only you will have at most one process to be there. Yeah. But so I made it to be extremely trivial here by making the critical region contain only exactly one statement. Yeah. Yeah, but the important thing is you will have to ensure that turn is one process waits on turn is equal to 0. The other process waits on turn is equal to 1. And then you ensure that each process flips the value of the turn variable at when it just before it leaves the critical section. Okay, so that is the idea here. So each process here can now be modeled using the rules of a sequential program, except that now you have a special construct statement called wait, for which I already showed what the piecewise transition relation is. The rest of the thing, I'm using the same rules that you saw in our earlier class as to how you would compose the construct the transition system for this sequential process. Each sequential process, there are two of them here, P1 and P0 and P1. Okay, so I've done you know, in a parametric way. So it can either be at Li, in which case you will do the while, you will check the while condition, and you enter NC, the NC location. Or if you are at NC location, then you will, if turn is equal to I, where I is 0 or 1, if turn is equal to I, then you will advance to the critical CR location, and nothing changes. None of the variables change. Or if you're in the critical section, yeah. See, if you're in the non-critical section, there are two possibilities. One is either turn is equal to I and turn is not equal to I, and that is captured by the second and the fourth disjunct. If you are at NCI and if turn is equal to I, then you will advance. If you are at NC but turn is not equal to I, then you will stay there. Okay. If you're in the critical location CRI, then you will just modify the turn by I plus 1 mod 2, and then you advance. Okay. What is the final one? Okay. Yeah, I mean the final one, the final disjunct is there because while loop has a disjunct corresponding to the exit part. Okay, but that is not possible here because this is an infinite loop. Okay, so each process is an infinite loop, and that's why you have false, and so this one is redundant. Okay, but I'm showing that only because the while rule will have an exit path, which in this case is not feasible because of the loop condition is forever true. Yeah. So what we need to do is to capture this spawning of the two threads, which is done by the co-begin statement, and that's what we need a rule for. Okay, that I will show in the next slide. Yeah, I mean the initial state we assume turn is bool initialized to some arbitrary value, and PC0 and PC1 are both at location L0 and L1 respectively. So the objective here of this program is to show that that it is safe. Okay, all these notions of properties will be formalized later on, but I'm kind of introducing them informally just to motivate this example. What we need to show the properties that the combined transition system here ought to satisfy are two kinds of safety, that P0 and P1 must not be at the same time in their critical locations, CR0 and CR1. Okay? And there is also another property in such parallel programs that you desire, that they are starvation free, that each process does not get denied access to its critical section indefinitely. Okay, that there is progress. Each process makes a progress. Okay, these are some, usually there are two kinds. This is called a liveness property. Okay, the first is called safety property. Whenever in any concurrent program, there are your two kinds of properties. One, we say something bad does not happen. They are called safety properties. And something good eventually happens, and they are called liveness properties. Okay. So now the question that we are addressing is, how do you construct a symbolic transition system for this, given the individual transition systems for each of the sub-processes here? And I already showed you earlier. Yeah, if you have any questions, I'm just going ahead. You can stop me. Yeah.
Yes, sir. I have a question.
Yeah.
Our objective is to ensure that P0 and P1 must not be in the critical section at the same time. But I think there is one possible way that they can be at the same time.
Let's get to that. Okay. Let's get to that. Okay. So hold on to that question. I claim that it is not possible, and I'll show you the combined transition system. And if indeed what you're saying is correct, then my combined transition system that I construct is see, when I construct the transit. Okay, informally, let's hold on to that question. Okay, because it can be you will be able to maybe argue why that is possible. Okay, based on this. First, I will address what is the combined transition system look like. Okay, so here. So obviously, we are taking the cross product of the two things. So here, What is the state universe for the individual process? Like I said, it is PC, the PC, and the state variable. Correct? Excuse me. Yeah. Okay. Yeah. So, firstly, the combined state variable will be. I haven't shown that. Okay. So let me show that. So my combined state. I mean, what I mean by combined state, I mean the state. I showed you earlier. It is S cross S. Each process will have PC cross the state variable. So each process will have its own PC, which is its local state. So the PC, in this case, that's the only local state component for each process. Turn is the shared variable, and there's no other shared variable. Therefore, the combined state of the composite system will be, I mean, the transition relation will be over those cross products. So you will have PC, PC0, the PC of the first process, and PC of the second process, and which are the local components, the only local components here, and the shared component turn. So there'll be 3 state variables in for the composite system: PC0, PC1, indicating the individual locations that each individual process can be in, the locations individual processes can be in, and the value of turn. Yeah. So this spawning of process is what is captured by this cobing. So this is the statement corresponding to. So if I can either, yeah, if I'm at location M, I can, yeah, now I can, I mean, yeah, after that I'll spawn these 2 processes, which means that, so this cobegin itself does not change any locations. So it can either make this go to L0, make the first process go to L0, or I can make the second process go to so I can either do this, spawn one process. I mean, either of I can spawn either of the processes. Okay, that's what this thing says. After that, so then it is just a disjunction of all of these things, which will capture the effect of scheduling, interleaving any of the individual statements. Okay, so the cobegin itself is captured by making by making the location go to P0 or P1. So what we have is, initial state is turn is bool. In it is PC0 is either L0, and PC1 is at L1. Okay. Yeah. So this we already seen. So my combined transition system will be defined as per this one. Okay, I think I have not exactly shown the, yeah, this is the transition relation that I've shown here, which exactly corresponds to this one here. So that's what I did, yeah. When I see, it exactly corresponds to this. So which is what is captured by this statement here. Okay. So either I'm at L0 or L1. So that's what I'm capturing. So when I draw this, the transition relation corresponding to the combined thing, what you'll have to do is you have to interleave. You have to take care of. You have to interleave these transitions one individually, one at a time. So for each, so the initial state will be, the combined initial state. Okay, whatever the initial state that you that you assume. So here you can. I'm saying that you can be either turn is 0 or turn is 1, and both processes are at their entry points. Okay. I'm sorry. I mean, you're starting with. I mean, you're not even there. After that, you can go to turn 0. That is the co-begin. So you spawn the first process. Okay. I mean, you spawn the two processes. First, you're in a state where you haven't spawned the processes. Then you have spawned the two processes, and both are at their entry locations. Okay, L0, L1, because I'm allowing for the possibility of turn being either 0 or 1. That is my initial state. After that, I'm constructing since this is a disjunction, the transition relation. So I have the two possibilities. From here, I can either choose to schedule process 0, in which case I'll advance L0. I'm sorry, schedule process 1 and advance process 1 from L1 to NC1. Okay, or the other possibility is I can take the other disjunctions corresponding to the case of scheduling the other process, the process 0. Okay, because you see this part going from L0 to NC0 is unconditional. Okay. But since I'm choosing one process, I can do this or this, yeah? And that return is equal to 0. Similarly, I'll have a copy of exactly this part with turn is equal to 1. After that, once again, so each transition here corresponds to the possibility of scheduling one of either one of the processes. So I can either choose to stay at choose to not schedule process 0, and then I can continue to schedule the other process. Okay, and that's how that you do. So you have the transitions here corresponding to all possible interleavings, and that is what is captured by OR. So I will stop here and take. Who was that? Was that Erumalai? Erumalai's question? Yeah. So let's spend some time and we'll revisit. So we are at 116. We are kind of a little bit, late, but since that question is fresh on our mind, so why do you say that? Okay, what is the scenario in which you think that both them can be at critical section?
Okay, I got my doubt clear. So what I thought was when we enter a critical state, I assumed that while entering the state, the turn variable will be made 0 or 1. I mean, it will be changed.
No.
Yeah, okay. That's what I assumed, and then I thought there is a way to.
That's not happening. Okay.
Yeah, the transition graph is clear.
Yeah, turn remains the same. Of course, turn could be either 0 or 1. So if it is 0, then the transition from L0 to L1, you can either go first schedule this and so either of them can end up in
yeah, only when we exit from a critical state, the turn variable gets
that's
changed.
when turn variables change. And that's why, and you will see that I mean, this shows only the reachable part of the states, okay, not the entire, okay. If you take, there are other states that are missing here, and I've not shown them here, okay, because you have to take the all possible thing for PC different, and there are, so obviously there are states here, potential states in which process 0 can be in CR0 and process 1 can be in CR1, and they're not shown here because they're not reachable from these initial states because of the way that the weight semantics works. Okay, so then I will raise the question. So firstly, by next class, I want you to review the combined transition relation, okay, that I have defined here. Expand it out by instantiating L is equal to 1 and 0, so it will be clear, okay? And then convince yourself that this indeed is the transition system diagram for the composite system as per this transition relation. Then I want you to answer these two questions based on this. Is the system safe? And is the system starvation free? The sense that is it possible that one process can indefinitely denied access to its critical section? Okay, so please do that review, and we will finish discussing this example next time. Yeah, that's where I want to end today, and I will stop here and take any general or specific questions that you may have for that until what we have discussed so far. Any questions? Okay. So then please do review the example before next time, and we will so I'm going to stop recording.